Okay, so today we're talking about weak acids and bases and buffers. So all of our other lectures, our first two lectures here, very specifically, were on strong acids and bases, and we had to memorize which acids and bases were the strong ones, right? You guys got those down yet? Look at these ones. Let's see. So again, the ones you guys need to memorize are just the strong acids. So there's a list of 6 in the top. And strong base right here. You guys should already be familiar with the hydroxides as a strong base because we already looked at hydroxides as bases back in chapter 5. And then for the acids, note that 3 of these just come from the group 7 elements, iodine, bromine, chlorine. And then you've got 3 of your polyatomics. Your nitrate makes nitric acid, sulfate makes sulfuric acid, chlorate here as well. So there's those 6. Those will all dissociate 100%, meaning that if I stick this in water, hydrogen iodide plus water, what I'm going to get is completely dissociated hydrogen plus the iodide ion. And if I'm in water, actually it's more appropriate for me to express that as the hydronium ion, right? And we talked previously about how that hydronium ion is essentially identical to the hydrogen ion. You guys with me here? Anybody? One of you? 2 of you? Yes. Okay, excellent. So the rest of these, as weak acids and weak bases, will do what we call partial dissociation. So instead of, let's say, hydrogen iodide, let's say we're using hydrogen fluoride. So hydrogen fluoride, if I put this in water, I will get some dissociation, but it's in equilibrium because not all of it dissociates. So a little bit of it will dissociate, and then they'll come back together, and then some others will dissociate till you get an equilibrium mixture of hydrogen ions, fluoride ions, and the combined HF molecule. You guys remember equilibrium back from chapter 7? A little bit. This is hydrogen fluoride. It's already dissolved in water, so we could have this dissolved in water. Some of it will dissociate. Now, because you have ions dissociated, both of these are electrolytes. This would be a strong electrolyte because you have many more ions in solution, and this could be a weak electrolyte because we have fewer ions in solution. Just a reminder, electrolyte means you have ions in solution. Okay. And if we get this equilibrium system here, we can express the amount by which this does dissociate by looking at the equilibrium equation. What would the equilibrium equation look like for this reaction? You guys remember that from chapter 7? You need to reach way back in your brain. Perfect. Yes, Joyce is exactly right. We always put the products divided by the reactants. So here are my products in this concentration. My H plus multiplied by concentration of my F minus divided by concentration of my HF in solution. Excellent. So the strength of any of these acids can actually be expressed in part just by looking at the K value, which, because it's an acid, we're going to call it a K sub A value. So it's an acid dissociation constant that's not really any different than my normal K, except that with that little a, I'm trying to tell you that this is equilibrium for an acid, for a weak acid. So my acid dissociation constant tells me, for instance, how much this will actually dissociate. So for example, in your lecture notes, I give you guys the K value for acetic acid, this one right here. Acetic acid has an acid dissociation constant, which then would represent the amount of hydrogen ion multiplied by the amount of acetate ion divided by the amount of dissolved but undissociated hydrogen acetate. This K value is about 1.75 times 10 to the minus fifth. That's pretty small, but it is enough to make it measurably acidic. And it tells us that you've got about, for every one molecule that does dissociate, one molecule that does this, you've got about 1,000 molecules that stay undissociated. So you can see why we call this a weak acid, because it doesn't dissociate completely, it only dissociates a teeny bit, but that teeny bit is enough to make it measurably acidic. And if we wanted to see how much that was, we could actually just solve for my H plus ion here. Solve this equation for the H plus ion, and then plug it into our pH equation and discover what the pH is going to be for our acid with the concentration given. Does that kind of make sense? You guys think you might be able to solve for the H plus there? Not yet, but you will in the end. Good question. First off, we just want to solve for H plus. So note here, and maybe this is a little bit messy because I'm talking about an actual thing. Let's look at a general equation for an acid. Has a hydrogen to donate, and then A is the conjugate base, some hydrogen with some acid A. So for instance, for HF, A is this F minus, and for my acetic acid, A is my CH3COO minus. Okay, so HA will dissociate to form the H plus and the A minus. And my K is my product divided by my reactants, right? So to solve for H plus, in this equation, I'm not plugging numbers in, I'm just going to solve for H plus. We need to get H plus on top and alone, and it's already on top, so we just need to get it alone. So we're going to then multiply by HA and divide by A minus on both sides. And I hope you guys can see how that's going to cancel out your A minus and your HA. So it's just algebra. And we find that then my K value times the concentration of my acid divided by the concentration of my conjugate base, that's going to equal my concentration of my H plus ion. Did everybody follow that there? Okay, now here's where this gets really fun and interesting, is in the creation of a buffer system. Okay, weak acids and weak bases, we understand that they dissociate a little bit, but when we make a buffer system, what we do is we put a weak acid or a weak base in a solution with its conjugate base, or if I was adding in a weak base, I would put it in with a conjugate acid. In other words, I am putting in the solution here, I'm dumping in a little bit of HA, And I'm also independently dumping in a little bit of A minus. Maybe I put in sodium salt of that conjugate base. But really, I don't care about the sodium because it's not acidic or basic. So by putting in the sodium, and I'm putting in a little bit of that conjugate base. Buffer system has both of these, and because this is an equilibrium equation, I should show this as an equilibrium equation, then we know that adding HA is going to push some of that HA this direction and have a little bit of dissociation. Then also adding A minus is going to pick up some of that extra H plus and move it a little bit this direction. And what we get then is this system that's at a nice equilibrium and has both HA to work with and A minus to work with. And as a result, what happens is this system becomes very resistant to pH changes. Because if I add a really strong acid, which would normally push the pH down, right? If I add strong acid, then I'm adding H plus, right? If I add H plus, then it enters this side of the equation. It combines with my weak base and creates more weak acid. So instead of adding a really strong acid, like I thought, in the system, it's immediately converted to a weak acid, and so the pH doesn't change significantly. Or if I add hydroxide, then this strong base hydroxide will immediately react with the weak acid here, pulls off this hydrogen to make water, which is neutral. And then that will leave me with, that pushes this reaction this way, that leaves me with this weak base here. So instead of adding a strong base, which is what I thought I was adding, it's immediately converted to a weak base, and that weak base then prevents, again, a large pH change. So instead of having the pH go up by lots because it was a strong base, it goes just up by a little bit because it was converted to a weak base. And again, instead of having the pH plummet because I added a strong acid, it just goes down a little bit because that acid was converted to a weak acid. Okay, let me write out those equations for you. So if you add H plus here, then essentially what happens is that H plus reacts with your A minus that's available, and you get the weak acid. And if I add hydroxide, then my hydroxide reacts with my weak acid, and what I really just get is more weak base. You guys following me a little bit here? Conceptually, at least. This is probably where one of the points where this is going to intersect really well with your physiology and your nursing classes, because the blood operates in a buffer system with several different buffer molecules, which is very important because your blood carries proteins which have optimum activity at a very specific pH. So if your blood becomes too acidic, that's a really dangerous condition. If your blood becomes too basic, that's a really dangerous condition. Your body does a really good job of keeping your blood within the right pH range by manipulating buffers. You might have already studied a little bit. But in any case, okay, so help me along here. This is kind of fun. We're going to use this K equation here with this acid, right? Because so the K equation just came from the dissociation of that acid. We rearranged it for the hydrogen ion. So we have this equation. I'm just going to rewrite the exact same equation down here. My concentration of my H plus is going to equal the acid dissociation constant multiplied by the concentration of the weak acid that I put in solution divided by the concentration of the weak base that I put into solution. So whatever I put in here, these values, that's what's going to be used in this equation. Now, if I want to take it a step further, I can take the minus log of both sides to solve directly for pH. So the minus log of the H plus is the pH. Now, the minus log of this whole thing you have to remember the properties of logs. But if you do, you'll come up with this equation where we find that the pH is equal to what we call a pK of A. That little p just means the minus log, so it's the minus log of the K sub A plus the log of the A minus divided by the HA. That second equation is called the Henderson-Hasselbalch equation, and that equation is in your textbook. And it's just mathematically derived from this first equation given here. Now, on the exam, really either one of these is going to be appropriate, right? Because if you can solve for H plus, then it's trivial to plug that in to your minus log of H plus equals your pH equation to find your pH. So I'm going to give you this equation on the test. And the problems that I give you are going to be the most useful with this equation. But on the homework, and also just for the sake of kind of seeing what's going on here, it won't hurt to use this one here and there. These are both the exact same equation. I just took the minus log of each side to get here so I can solve directly for pH. And if I was given the pKa, then it would be easy to use that. It's probably been a long time since you guys studied logs and the properties of logs. So if you guys want me to, after class, I can go over the process by which this equation becomes that equation. I don't mind doing that, but it's not, because I give you the equation, I don't think it's really necessary to understand that for the exam. You guys trust me there? Joyce, trust me. That's good news. I'm never quite sure. All right, so let's do an equation here. Let's see if we can track what's going on. So let's say, for instance, we've got a buffer solution made with formic acid. So I'm on the lecture notes on page 3 right now. So I have a buffer solution made with formic acid, which is HCOO8. Oh, it's a different color. Here we go. Formic acid, which naturally dissociates to acid and HCOO minus. Okay. And I've got 0.056 moles of the formic acid that I put in there. And 0.056 moles of the conjugate base. A really good buffer is going to have the same amount of both your acid and your conjugate base, because that way it'll buffer both directions of changes. But let's say, okay, we've got 0.056 moles of each of those in solution, and I'm given that the acid dissociation constant for formic acid is 1.8 times 10 to the minus 4th. So then the question is, what is the pH of this buffer system before we do any changes? And we can just plug in the numbers that we have to our equation. If I gave you the Ka, then you might say, let's use the equation that has the K sub A. That's going to make my life easier. So I know that my acid concentration is going to be the K sub A, which is 1.8 times 10 to the minus 4th, multiplied by the acid concentration. Now, which is HA? Which is my acid here? Yeah, this is my acid. Or in other words, this is HA. And this is my conjugate base. Again, this is what we did at the very beginning of this chapter, was identifying what's my acid, what's conjugate bases. That's going to be important for this section. Excellent. Okay, so here's my acid because it has an extra H right here. So that's going to be the HA. So I'm going to have 0.056 molar HCOOH divided by 0.056 molar HCOO minus. In this case, it might not have mattered because I had the same numbers, but they're not always going to be the same. So we want to make sure that we follow that. So what I want you to know, if these are really the same amounts, they almost cancel out, and we find that the H plus concentration is 1.8 times 10 to the minus fourth. Did everybody follow me there in plugging in these numbers to the equilibrium equation to calculate my the acid concentration? Okay. Now, if I wanted to know the pH, what would I do next? Take the minus log. Perfect. Just plug it on in. 1.8 times 10 to the minus fourth. So the advantage of this equation is that it finds the pH directly, but I find that this one is just so much easier to use, and then it's trivial to find the minus log afterwards. That's why I have you guys use this one. I feel like it's more user-friendly, and I hope that you find that as well. So we just take the minus log of 1.8 times 10 to the minus fourth, and we do that. 1.8 times 10 to the negative fourth, and then I'm going to take the log of that, and then the minus log of that gives me a pH of 3.74. So this is a weak acid, but it's still on the acidic side of the pH scale. I mean, it's still measurably acidic. It's a wide range here. Everybody follow me to that point. Excellent. Okay. Now we're just going to take it. Great question, Sana. I will either give you a K value, or I will give you all of the other pieces and ask you to calculate the K value. One or the other. But you'll always have, either the K value or the concentration units to determine it. Yes. Okay. Now, let's take it one step further. I've got this buffer system with a weak acid, and it dissociates naturally, and I added both this weak acid, this much of my acid, and this much conjugate base. Now, to this system, I want to add sodium hydroxide. I'm going to add 0.013 moles sodium hydroxide. And the question is, what is my new pH? What is my new pH after adding 0.013 moles of sodium hydroxide? Now, important thing to notice, I'm not adding sodium hydroxide to pure water, right? Because if I add the pH as if I added this to pure water, then I'm going to get a really basic solution because this is a really strong base. But I'm not adding it to pure water, I'm adding it to a buffer system, and the buffer system is going to react with the sodium hydroxide. And in order to track this, you might use what we call an ICE chart, which says, okay, looks at the species that we've got in solution. So we've got our acid, and we've got when it dissociates into the hydrogen ion and the HCOO minus ion. And now we're also adding sodium hydroxide. These are the four things we're looking at. So initially, before I've added anything, I have 0.056 moles of this and 0.056 moles of that. Okay, actually, I'm not going to track this because that's what we use this equation for. And we've got 0.013 moles of sodium hydroxide. That's what we've got initially. Oops, I could draw a straight line. What does the sodium hydroxide react with in my buffer system? This is an easier question than it sounds like. Is sodium hydroxide an acid or a base? It's a base. Do bases react with acids or do bases react with other bases? Bases react with acids. Okay, so then which of these two things is an acid? That's going to tell you what the sodium hydroxide reacts with. Perfect, the HCOOH. Okay, so we can even write a little equation for this. We're going to recognize that the HCOOH is going to react with the sodium hydroxide. And what will the product of that reaction be? All right, Candace says we're going to get water and then we're going to get our conjugate base with the sodium hanging out. Anybody agree? Robin agrees. This is exactly right. The sodium really isn't necessary. You're in water, they're completely dissociated. So sodium is a spectator ion that we don't even need to really track. I'm going to erase it. Sodium is not as important to me as the hydroxide that's with it, okay? So the hydroxide is going to steal that hydrogen, because that's what bases do. They accept hydrogen ions. And that's going to make water, which really has no effect on the system. And then it's going to make HCOO minus. Okay. All right. So let's say we initially had 0.056 moles of this, and I added 0.013 moles of this, and I had 0.056 moles of this. That hydroxide, when it reacts with the HCOOH, is it going to remove some of the HCOOH from solution, or is it going to add more of it as this equation is written? It's going to remove. So the change here for the HCOOH is I'm going to remove 0.013 moles. Right? As this reacts, they remove each other, and in the process they're going to form, I hope you guys see they're going to form an additional 0.013 moles of my conjugate base. Okay, these two react together. The hydroxide doesn't use up all of the acid. It can only use up as much as there was of the hydroxide. And that's going to make that much more of my conjugate base. Did everybody follow that conceptual exercise? And by everybody, I need at least 2 or 3 of you. We've got 1 vote for yes. Okay, good. You guys are with me, or at least you're with me-ish. Just a good start. Hang on a second, and I'll ask you about that in a second, Robin. I initially had 0.056, and I have removed 0.013. Then I hope you guys see in the end, what I've got left is 0.043 moles of my acid. Here I had 0.056 and I've added 0.013, so now I have 0.069 moles of my conjugate base, and my sodium hydroxide has been used up. Okay. Now the numbers, where are the numbers coming from? These numbers were given, right? At the very beginning, I said this is what you had in solution. These were given. These are given. And that was what allowed us to calculate our initial pH. Then in the second case, again, this number was given. This is to say, if I added this change, if I give you this number, can you then incorporate that to the data that you already have and determine what you end up with in the end? With the numbers for the concentration of the numbers of moles, I'm not using a formula, I'm just handing you these numbers like I would on an exam. So initially, I told you that we made a buffer solution containing this many moles of acid and this many moles of conjugate base. So that's where these numbers came from. And then to this buffer system, I told you, 0.013 moles of sodium hydroxide. And so we put this to say, hey, initially, this is what we've got in our system. And then the important thing, kind of the hard part with buffers, is to recognize how adding this acid or base is going to affect a change. And so recognizing bases react with acids. So as the base is used up, it's also going to use up some of my acid. And in the process of using up that acid, as we did here, we're going to create more of our conjugate base. So that's why we subtract 0.013 moles from each of these. We add 0.013 moles here. And that gives us a final number of moles for our acid of 0.043 and for our conjugate base of 0.069. Now we have not yet plugged in any of these numbers to determine our final hydrogen ion concentration or our final pH. We just are determining what the new concentrations of our acid and conjugate base are so that we know what to plug into our equation. Did that help explain it at all, Robin and Megan? Okay, so this is the initial system that we were given. Initial system, buffer system, and now we are stressing our system in some way. So we can calculate the pH of our initial buffer, and now we're saying, what if we added a strong base? What if we added a strong acid? How would that change our pH? And I want to show you this because the whole point of the buffer is that it's resistant to pH changes. I want to show you kind of what that means. Okay. So at this point, we've just got new numbers. The whole point of this exercise was to give us the new numbers to plug into our buffer equation. So again, buffer equation that we're using, my H plus concentration is equal to my K sub A times my acid divided by my conjugate base. So for the purposes of this buffer system, which has had sodium hydroxide added to it, my H plus is going to be the K sub A, which again is 1.8 times 10 to the minus 4th. But that was given to you in the problem. Multiplied by my acid concentration. What's my acid concentration? Perfect, it was this one, right? Because this is my acid. My final concentration is 0.043 moles in a liter. And then my base concentration goes in the bottom, and that's this one, because this is my conjugate base, so 0.069. Okay. So we plug that in. We have 0.043 divided by 0.069. We're going to multiply that by 1.8 times 10 to the negative 4th. And we get hydrogen ion concentration of 1.12 times 10 to the minus 4th. Hang on a second, did I do that right? Should have done that right. Okay. Yeah, I did that right. Okay. So then now, how do we find the pH? take the minus log of that. Perfect. Log of that, negative of that. My new pH is 3.95. Now, first we need to make sure that this makes sense. I added a base, so my system should have gotten a little bit more basic. Did my system become more basic? Did that solution become more basic? Yes, it was previously 3.74 pH, and now it's 3.95 pH. The pH went up, which means it became more basic. Does everybody follow that? Just comparatively there. Okay. Now, is it a lot more basic, or is it just a little bit more basic? It's just a little bit. It went up by 0.2. Comparatively, if I just put 0.013 moles in a liter of hydroxide, if it was just water, that would give me a pH of 12.11. Okay. Huge pH change from 7 to 12.11 if I put this in pure water. But if I put it in this buffer system, because it was immediately converted to a weak base instead of staying a strong base, my pH just changed a little teeny bit. And that would be really helpful, useful, and important if you were a biological system that needed to maintain a very specific pH range. Do you guys see that, how that falls out? I just want you to look at this for another 2 minutes, and then we'll go look at the in-class activity sheet and do a little bit more practice. But if you're doing something that's got a change in it, like adding sodium hydroxide or adding a strong acid, using this, they call it the ICE table, because you have the initial conditions, the change in conditions, the end conditions, ICE. That'll help you track what's going on. And it's important to remember bases always react with acids. Acids always react with bases. Two bases don't react together, right? Because they're both trying to gain hydrogens. That's not useful for either of them. Two acids won't react together. So if I give you a base and you're like, I don't know how this changes the system, you just have to remember bases will react with acids. If I give you an acid, then you'd have to say, okay, the acid will react with the base. And you can write out that equation. Okay, let's do just a little bit of practice here. So we're in our 10.2 in-class activity sheet. We're on this last page. And I'm going to skip section 4 for a minute. We're just going to look at section 5 and 6. Okay. So for section 5, I'm not asking you to do any changes. I'm just giving you the data and asking you to tell me what the pH is. And then in section 6, we are doing a little bit of a changing by adding sodium hydroxide, or kind of determining how much of an acid must be added to get your pH into the right place. Okay. So section 5 is just to plug it in. What's the equation we're going to want to use here? There's no changes. I'm just giving you a buffer. Excellent. For this equation, this is the one I'll give you on the exam, right? It's on your equation sheet. Your H plus concentration is equal to your K sub A times your HA divided by your A minus. Okay. And I give you the value of K sub A for each of these. So that's for section 1. This is for section 2. This is for section 3. And then I give you a system. Can you guys look at these and figure out which of these is the acid and which is the conjugate base? Like, let's look at section 2. We've got a system with ammonium chloride and ammonia. Which of those is my acid, or HA? Which of these is my conjugate base? Okay, you guys are all exactly right. For the first case, as Megan pointed out, my H2PO4 minus is my acid, and then my HPO4 2 minus is my conjugate base. In the second section, my NH4Cl is my acid. That's going to make my NH3 conjugate base. Okay, good. So you guys are good at identifying those. And I've given you the numbers, so this is just a matter of plug and chug. What happens once you find out the H plus concentration? Then what do you do? Minus log. Excellent, because the pH then will be the minus log of my H plus. Okay, so if we did that, let's say on this first example, we're just going to plug this in. H plus equals my K sub A, which is given right here, 6.2 times 10 to the minus 8, multiplied by my acid concentration. You guys told me that acid was H2PO4 minus, so that's going to be 0.08 molar, divided by my conjugate base concentration, which we said was HPO4 2 minus, so that's 0.12 molar. So in that case, oh, Sneeland, you might just be like way ahead of us here. 0.08 divided by 0.12 multiplied by 6.2 times 10 to the negative 8. That gives me an H plus concentration of 4.133 times 10 to the minus 8. And then my pH equals the minus log of that, which then take the log, make it negative, and I get a pH of 7.38. Candace is like way ahead of us here. Excellent. So my pH was 7.38. Everybody feel comfortable with that? Megan, are you at least with me on this section? Robin, are you with me on this section? Excellent. Okay. And parts 2 and 3 are exactly the same. All right, you're using these two equations, both, and you're just plugging in these three numbers that I will just give you. And the hard part then is just identifying which of these is my HA, which of these is my A minus, or which is the acid, which is the conjugate base. Okay, so you guys can do this. Oh, look at me, look how rude I was. What are you gonna have to do here? Yeah, give you grams. You're gonna have to go to molarity. That was just rude. But you can do it. You guys know how to go from grams to molarity, right? Or grams to moles. In fact, I'll let you guys in on a little secret. This is concentration units, which is supposed to be molarity. But since it's the same solution with the same volume, the volume cancels out and you can just use moles directly. Yep, you do. It's rude. So just convert to moles, and it's in 1 liter, so the moles is the same as the molarity, but for some of these down here, we can actually not worry about the volume and the concentration and just use moles. Anyways, I will let you guys do these other ones because I think you can, and I think it's good practice. So I'm going to let you guys do it, and I'm going to work through section 6 because this is where it gets harder, okay? Section 6 is actually exactly the same as section 5. It's just that by adding an acid or a base, we're going to change the concentrations of my HA and A minus before we plug them into these exact same equations. So the last few steps are going to be exactly the same. I'm going to identify my concentrations, plug them in, convert the pH. But first we have to say, how will this affect my concentrations that were initially given? Okay. So this is buffer system. I've got H2PO4 minus and HPO4 2 minus. So what is my acid and what is my conjugate base in this equation? Excellent. H2PO4 minus is the acid. And then my HPO4 2 minus is my conjugate base. Excellent. And here I'm given the pKa of the acid is 7.21. But you also see it's the same system I had up here. So if I wanted to use just the KcalA, I could do that. 6.2 times 10 to the negative 8th. Okay. So this is kind of initial conditions. So let's write this out so we can see what's going on. My acid, my HA always dissociates to form my H plus and my conjugate base, right? So if my HA is H2PO4 minus, I could say I have H2PO4 minus dissociating to form the H plus and the HPO4 2 minus. Did you guys follow me here from identifying the HA and the A minus to actually looking at the equation where that HA dissociates? I'm just looking back at my initial equation and defining, okay, this is that, and this is that. Anybody else with me, or is it just Candace? You're on a roll today, Candace. You're doing awesome. Okay, so initially we start out with, it says 0.02 moles of the H2PO4 minus, so 0.024 moles of this, and 0.024 moles of this. Okay. And now it says I have added 0.012 moles of sodium hydroxide. What is sodium hydroxide going to react with? The acid. Sodium hydroxide, the base. Bases react with acids. The acid is this that you guys defined as HA. So it's going to react with the H2PO4 minus. And when it does that, what's it going to make? More of the HPO4 2 minus. Excellent. All right, so we've got 0.012 moles of this. How many moles of the acid is this base going to use up? Like 0.012 moles of sodium hydroxide is going to react with how many moles of the H2PO4 minus? It's the same. Because 1 mole of this reacts with 1 mole of that, so 0.012 moles of this will react with 0.012 moles of that, and that's going to make 0.012 moles of this. Okay, so if we put this in an ice chart so we can see it a little bit more clearly, we have my acid, we have the conjugate base, and we have my sodium hydroxide. This problem is taking up more space than I've got here. I apologize. Okay, so initially, change, ending. Initially, I have, and this is what's given right here, 0.024 moles of each of these. And I added also 0.012 moles of sodium hydroxide. And then because we recognize the sodium hydroxide will react with the H2PO4 minus, then we are losing my H2PO4 minus. I'm losing that as I lose the sodium hydroxide as those two react together, and that's going to give me 0.012 moles of that. So in the end, I'll have 0.012 moles of my acid, I'll have 0.036 moles of my conjugate base, and I have no more sodium hydroxide left in solution. Okay, and just as a reminder, this is H2PO4 minus, and this is HPO4 2 minus. Okay. Do I have at least 2 or 3 of you guys with me here? It's the same point that I have on the other page, Megan. So am I losing you when I react it with the sodium hydroxide, or am I losing you when I try to put it into an ice chart? Gotcha. I hear you. So well, and maybe you don't want to put it into a separate thing. If you're going to say, recognize the sodium hydroxide is going to react with the acid, you could say, let's put the sodium hydroxide here. So that's going to consume some of that acid and push it over to that direction. I don't know if that helps make sense, but that's essentially what you're doing it. Or if we could look at this conceptually, we've got a pot here. We've got a solution. That's okay, but I don't mind putting this out here as well. We have some H2PO4 minuses here. That's my HA. I've got some HPO4 2 minuses hanging out here. And if I add a hydroxide to the solution, then it's going to encounter, this is more acidic than that, so that hydroxide is going to steal one of those hydrogens. When it does so, it's going to become water. And this guy's going to lose that extra hydrogen. And it's going to become a 2 minus. So by adding the base, now I have more of my conjugate base than I did before. These are my conjugate base. And I have fewer of my initial acid that I had to start. Does react mean reduce? Yes, if you're talking about reduce as in subtracting the amount that's there, yes. So by reacting with the H2PO4 minus, I'm removing it from solution, just like I did here. By reacting with it, now it's gone because it's not there anymore. And then by reacting with it, you'll find that it produces more of this other thing. So you'll see once I stole that hydrogen, now I've made more of my conjugate base. So maybe follow this kind of conceptual thing. That's what I'm trying to show here in this equation, these two equations. Okay, so now we have new numbers to plug into our equation, and we're back to this point, just taking the numbers that we have and plugging them in. And we can do that. But let me ask you guys, you are given the pKa and the K sub A, so you guys can choose. Would you rather use this equation on the left, or would you rather use the fancy Henderson-Hasselbalch equation on the right? Because you're given the pKa, so we could just go straight there. Use the pKa. Okay, so the pH will be equal to the pKa plus the log of my A minus over HA. Here we go. So my new pH is equal to the pKa plus the log of my concentration of conjugate base divided by concentration of my weak acid. So the pKa was 7.21. What was given up here? And I'm adding the log of my A minus, which is 0.036, divided by my HA, which is 0.012. And now I just plug it in and calculate it. That should give me my pH. Okay. Here's my calculator. By the way, you guys should all be doing this on your scientific calculators just because you want to make sure that you're using them correctly before you get to the exam again. Because the way they use logs are sometimes funny. So 0.036 divided by 0.012. And I'm going to take the log of that. And I'm going to add that to 7.21. And that gives me a final pH of 7.69. Did everybody understand this last step where I just plugged in the numbers that I got? Okay. And again, if you wanted, you could have just used the H plus is equal to the Ka times the HA over A minus. And then taking the minus log of the H plus to get the pH. You'll get the same exact answer. Okay. This is the culmination of everything that we've talked about in class. Okay. You'll see we've got multiple ratios here, recognizing what's happening as we react these things together. We're talking about equilibrium equations and the K values for equilibrium equations, manipulating those, and then we're plugging those into our log equations to find our pHs. So it's, a little bit of chapter 6, a little bit of chapter 7, a little bit of chapter 9, because we're using solution concentration units, extra from chapter 10, rolling it all together in one awesome, fun ball of chemistry. This is the hardest that it's going to get on the test. It doesn't get any harder than this. At least in my opinion. I don't know. You might be struggling with something else, but this is it. Really, really. Okay. But recognize, I mean, just so many pieces come together here. And at this point, actually, because you've been studying each of these pieces for the whole semester, it's not as hard as it might think. But if you stop to look at it, I could give you grams and expect you to go from grams to moles. If you have moles and you have volume, you can find concentration units. If you recognize this as a weak acid, you've got an equilibrium dissociation here. And if you add a strong base, the base will react with an acid, and you can predict how that's going to change the relative ratios of your weak acid and your conjugate base. Or if you add a strong acid, other direction there. How's that going to affect your equilibrium? The next one, okay, well, we'll do the next one. It's the same, the next one's the same type of problem. I just ask it backwards, but it's the same type of thing. Okay, I'm actually going to erase this so that we've got space to work on that one. Okay, so I've got a buffer, 500 milliliters, a buffer special system contains blah, blah, blah. Okay, so first of all, what's my acid? What's my conjugate base? What's my K sub A or pKa? Excellent, NH4 plus is my acid. Recognizing which your acid and base is important here. And then my conjugate base then must be my NH3. And they gave me here now a K sub A instead of a pKa. So I'll write this down. 5.6 times 10 to the minus 10. Okay. And we want our target pH. Ooh. Target pH needs to be 9.25. And now we're going to say, in order to get there, I need to add strong acid, add HCl. Okay. Well, okay. First, let's write out our equation for the dissociation of our conjugate of our acid. So we've got, it's always HA dissociates from H plus and A minus. So my HA is my NH4 plus is dissociating to form my H plus and my NH3. Everybody with me so far? Okay. Now, if I'm adding HCl, is that going to react with the HA or the A minus? It's going to react with my ammonium or my ammonia. The base. Because HCl, this is an acid. So acids react with bases. So the base here is my A minus, it's my NH3. So we're going to say we've got a buffer system that's got some of each of these. And then I'm going to add some HCl, and it's going to react with the base, because acids always react with bases. And when my HCl reacts with my base, what am I going to get? More NH4. It's exactly right, right? This is my base. It's a proton acceptor. So it's going to pick up a hydrogen ion. It's my acid because it's donating a hydrogen ion. So I'm going to end up with more NH4 plus. And Cl minus, but we don't care about the chloride. This is a spectator. Does nothing for me, so I'm not even going to worry about it. What I do want to know is how adding the acid affects my relative ratios of my conjugate base and my weak acid, because I started out with 0.059 molars of this, right, given here, and I started out with 0.1079 molar concentration of this. Got that right here, 79. So if I add X amount of HCl, then what's that going to do to the NH3 that I've got in solution? What's that going to do to the NH4 plus that I have in solution? Well, Joyce already answered my question. She's on top of it. I'm going to add X amount of NH4 plus, because it's in the process of reacting, it's going to go that direction. What about my NH3? It will be less by the same amount, okay? Because I stick HCl in solution. As it reacts with the NH3, it uses it up to make more NH4 plus. So if I make an ice chart here, and we've got my HA, which is my NH4 plus, and my A minus, which is my NH3, and then the HCl here. Now I made those X's because that's what we're asking. That's what we don't know. How many moles of HCl? And actually, I'm going to change this problem right now so that the answer is not going to be the same as on the key. I'm going to make this 1 liter just to make it easier, because the concentration, yeah, I wouldn't give you 500 milliliters on the test. Okay, so we're in 1 liter, so that number of moles is the same as the molarity. So if I start with 0.059 moles of this, and 0.1079 moles of that, and X moles of that. The change then, we determined I'm going to add more here. I'm going to subtract the same amount here, subtract the same amount here. It's going to use up all my HCl, and I'll have 0.059 plus X here, and 0.1079 minus X there. Everybody roughly follow me here? Megan, this might be the same point that you departed at last time. The difference between these ones and the last ones is that because we're adding an acid, then it reacts with the base to give us less base and more acid. In every case, if I add a strong acid, what I really end up doing is getting more of my weak acid, HA. And if I added a strong base, what I really end up getting is more of my weak base, the A minus, is the point of the buffer. Okay. Now we have all of the pieces, we can plug them into our equation. And since we have the case of A, we'll probably want to use equation H plus equals my case of A multiplied by my HA divided by A minus. Now we've got the case of A. We have the HA and the A minus to plug in. What's my H plus? Where do I get that from? Perfect. In the first one, I had to calculate the pH. So once I found my H plus, then I took the minus log of it. Here they gave me my pH, so now I just have to go back from the pH to the H plus. 10 to the negative 9.25 should give me my H plus concentration. So here we go. 10 to the negative 9.25 is equal to 5.6 times 10 to the negative 10th, that's my case of A, multiplied by my HA, 0.059 plus X, divided by my A minus, which was 0.1079 minus X. And now I solve for X. And I'll be done. Does this one feel a little bit harder than the last one? Sorry, I said the last one was as hard as it gets. This is essentially the same thing. I'm just looking at it from a different angle. But it is the same exact problem. We start with kind of the same data here. We have to recognize these same relationships here. The difference is instead of giving you X and having you calculate pH, I give you pH and have you go back and calculate X. But it is conceptually exactly the same thing. Okay, so let's do this. Let's say, here, let's solve here. So we're going to have 10 to the negative 9.25, this is just algebra, divided by 5.6 times 10 to the negative 10th, multiplied by, well, let's get to that point. This is going to equal 0.059 plus X divided by 0.1079 minus X. It'll be easier to do step by step. So 9.25 negative, 10 raised to that, divided by 5.6 times 10 to the negative 10th. Ooh, 1.00418, or 1. 1 is equal to 0.059 plus X divided by 0.1079 minus X. So now I'm going to multiply both sides by 0.1079 and I get, sorry, by 0.1079 minus X equals 0.059 plus X. Is that what you meant, Jay Houston, that by these two canceling? Because yes, they do. They essentially canceled down to 1. Yep. And that made our problem a little bit easier, didn't it? Because then we didn't have to multiply through kind of here. We just could move this denominator over to the left. Okay. And then to solve for X, I'm going to add X to both sides. So that's going to give me 2X on this side. I'm going to subtract 0.059 from both sides. So I'm going to get 0.1079 minus 0.059. And that is 0.0489. That equals 2X. So if I divide by 2, then X is 0.02445. That would be moles of HCl. Now the initial question actually was in 500 milliliters. So if this was my molarity, then to go backwards to moles, I think we'd end up with 0.012 moles of HCl, but that's an extra step I don't want you guys to have to do. There is, I think, a problem like this on the homework, very similar, which is, I think, where I stuck this problem in the in-class activity sheet. So have a look at that. And that is, I believe, as hard as it's going to get. Really, really. In fact, yeah, the other section of this in-class activity sheet, up here, gram equivalents, just don't even worry about that. I won't test you on that. It's not. You don't have to worry about it. One last thing. That's it for chapter 10, guys. I'm going to stop this recording.